welcome our first speaker in this session. Applause. The floor is yours.
Yeah. Hello, I'm Artur. This is spontaneous, so it can be a little chaotic. If you don't understand something, just interrupt me and ask questions. This will be, unfortunately, not in Rust. However, in one of the future meetups, I was thinking about preparing it as a live demo in pure Rust. I guess everybody knows what is Linux. Did anybody here read the source of Linux, like the kernel itself?
Well, what do you mean by read?
Like, at least looked at it at some point. Okay, so, and did any of you try to modify it? Oh, nice. We've got two people. If you want to modify it, you can modify the source directly. You may also implement a module. And while doing so, you need to be careful because you can break the kernel. Linux maintainers introduce a mechanism that allows you to load code to kernel at runtime. So you don't need to recompile the kernel itself. And it guarantees it's safe, that it will not like hang, loop infinitely, crash, and so on. So, did anybody of you have heard about eBPF? Oh, nice. Maybe I will may I pull out of myself. But yeah. So the idea with eBPF is that you implement some code that will be loaded into a kernel. It's being compiled down to special bytecode that later, upon loading to kernel, Linux verifies that it will terminate in finite amount of steps, which means it's not Turing complete. And also, it checks all of the memory accesses, so it makes sure that it will not harm the kernel. Let's see an example. Here, I wanted to add a custom syscall. So, how many of you know what syscall is? Okay, I guess like most of you. So, in very short, briefly, if you want to ask operating system to do something, you do that through the system call, abbreviated to syscall. Let's say that we want to have an example of a syscall that basically counts how many times it has been called and tells you that number. So here, this example uses BCC framework, which is no longer like the way to go, but it is what it is. So the way to write eBPF applications, you need two components. One is what resides actually in kernel, runs there, and so on. And the other one is user space that loads the kernel part into the kernel. And here we can see on the left the example of the loader. This is like actually pretty simple. You just specify the program. It's like in C that is being loaded to kernel, and it just compiles it, runs it, and there is like long sleep. It could be like infinite loop or whatever. So pretty simple on the user space, pretty minimalistic. In terms of what is being added to the kernel space, we define our syscall number. Then we define some hash map that resides between like when the program is like loaded to kernel. And it maps 32 bits number into 64. 64 is our counter. 32 bits is the process ID. And in kernel space is like a little bit tricky since what we know about threads and processes is like slightly different in kernel space. we call thread a process in kernel space, and process from user space we call it a thread group in kernel space. So here it's actually the PID actually denotes what we know as thread. And then we define our syscall. It takes a pointer to where we are gonna write back the current value of the counter. And here we specify trace point probe. So there are like different types of BPF programs, and they allow you to plug in into different places of Linux kernel. You can actually plug in into almost everything. Here we decided to plug into sysenter, which is called whenever some syscall is being entered. So what we do, we just check whether the ID of the syscall is our syscall number, and then we just take the argument for the syscall. So we just take the first argument, which is the buffer, into which we write our result back. We invoke the syscall, and inside of the syscall, first thing we get the PID. Then we address our index our hash map with the PID, get the pointer to the value, we increment it by 1, and then we write back to user space through the pointer we got as an argument. So this way, every time we invoke this syscall, it increments the number and returns the current value of the number. And then I can also see there is another thing that flags in when the process exits, and it just removes, like cleanups the hash map, so that when the process actually, the thread exits, we clean up it so it's not like memory leaking inside of the kernel space. And then there is a simple, oh wow, why did it become so bright? Whatever. And then there is a simple usage. This is like a regular process, which is like not related to the user and kernel space, where we want to actually invoke our syscall. So we get a handle to libc. We create some buffer into which the value will be written back. And then we just do libc.syscall. So we do like arbitrary syscall with our number and buffer as an argument. And then we get the result print back. And since it's a loop and we invoke it 16 times, it will be like counting 0, 1, 2, 3, and so on. So that's it. On one of the future meetups, I wanted to actually show this or some other example using pure Rust, because you can write both the kernel space and the user space in just Rust. There is a framework called Aya. And yeah, that's it. Are there any questions, or was something not clear and you would like to have it clarified?
The thing is that, as I understand, this will run for pretty much every single syscall.
Yes, if you would, some alternative approaches would be to hook into something else. For example, you can hook into some very specific syscall, and you could do hacks like if let's say file descriptor is -42, which normally is like illegal, but you could treat it as your entry point. You could, detect it as your entry point. And yeah, I agree, it is kind of hacky, but yeah, it is what it is. Normally what will happen here is that when we invoke something like that, operating system, will invoke our BPF program, but it will then continue with execution, and it will tell us that, hey, this syscall just does not exist, and it will return an error. So that is also why we are like writing to user space to kind of have some feedback. There is a way to override some return values but the kernel needs to be compiled with some special flags, and it is a security issue. Also, writing back to user space is not advised, since you can break user space programs. But yeah, it is just to showcase the ability to.
Another one, actually, I don't remember how, but how is this tracing?
That is a good question. I don't remember.
Trace works by separate system, which is also used by other debuggers. Essentially, you have three-phase system, which is for implementing debuggers, and it allows you to tell kernel that this process that you are tracing should be stopped on every syscall, and then the kernel should call you back.
I see. Yeah, because what I was doing a while back is I was trying to trace all of the syscalls but on Windows.
Mm-hmm.
That's it.
I see. I see.
And I read about it. I wonder whether there is something like this on Windows. I don't think so.
I don't know. I haven't like looked into Windows, so.
Windows has completely different approach to syscall.
Yeah, the way I was doing it.
That's also true.
Because so it would not call writes properly into the DLL like it's create file, and instead it would call it to my shell code, essentially my assembly, which would do what I want and then call the real function. And then it would go to syscall, the proper system.
Okay. Well, on Windows, as far as I'm aware, syscall numbers are like not stable, and you should go through the library functions.
They are stable since Vista, I think, on Windows 10.
Okay. Okay.
No, Windows 10, but the thing is, a lot of APIs on Windows do not use systems. Because Windows allows, for example, kernel to directly call back into interspace program.
Mm-hmm.
You can pass a callback to kernel, and the kernel will call back directly to interspace.
Mm-hmm.
That's, for example, the main difference between how signals work on Unix and how they completely do not match anything in Windows. Because on Windows, on Unix, you have only the signal mechanism as a way for kernel to call back into the process.
Okay.
And on Windows, you can simply register any normal function to be called back from kernel context.
Okay, so in Linux, if you have like fuse or something else, you're basically doing the app call. Is it through the signals?
No, you end up calling using IO control syscall usually. So you end up in a constant call. You call syscall and it's waiting.
Mm-hmm.
On Windows and on Windows NT, not on Windows in general, and on VMS, you can pass using a syscall, of course, a function with appropriate header, which can be called by kernel directly. For example, it's not exposed on Windows NT, but it was exposed in the previous, let's say, edition of the same mechanism in VMS. So you could, for example, instead of waiting for a log, you could tell the kernel, when this log is released, call this function in my code.
That is a lot to digest. I will need to have it explained slowly later. But it is interesting.
It's completely different world, and a lot of even terminology doesn't matter.
Yeah, let's chat after the lightning talks. I would.
Quick question.
Yes, of course.
I always wondered, I don't know what are the performance characteristics of eBPF, like, does it cost a lot to do pointer checks to the kernel, like, compared to, like, in general, it checks whether your code, like, so it doesn't go into wrong parts of the kernel, it doesn't crash the system, eBPF. And, yeah, to do that, it needs to check the pointer accesses and things like that. And does it introduce much in terms of performance?
So
You don't have the ability to pointer access.
But you still
No, you don't get access to kernel memory.
I mean, in BPF you can read the kernel memory, but you need to do that through the BPF helper functions, and they can fail. So you need to check for errors, and you have like limited access like without these helpers, and it is being verified when loading to kernel space.
I see, so you can only go to kernel through the APIs.
Yes, and there's like also a mechanism which is also quite interesting. So this uses BCC, which was really cool back then, but it has the issue that it is not really portable if you change the Linux kernel like quite widely. And libbpf came up with core, which stands for compile once, run everywhere, where in Linux you have BTF. I think it stood for BPF type format, if I recall correctly. Yeah, which basically records all of the types in kernel, including private ones that are normally not exposed, with like offsets, types, and so on. And then the libbpf, when loading the program, it has like kind of a linker where it patches the offsets to.
BPF is essentially the debug information simplified. It's you know how when you compile a C program with GCC and you compile with debug info, you get Word bytecode attached to it. This is describing every type, every function, everything. BPF is essentially take this Word, simplify it so it has only the type information and functions in nature. So it's much smaller, it doesn't have all the information, but it means you can relocate against the kernel without knowing everything.
Yeah, I was not like looking into dwarfs and what information is there. I have like rough understanding what BTF contains. Yeah, and you also mentioned performance. There are like different types of BPF programs, and it was like evolving. And there are like benchmarks if you like look on the internet how it looked. So initially there were like K probes and K-red probes. I think it was like C3 breakpoint if I recall correctly. I am not sure exactly. So you could like plug into like almost any kernel function. Later they introduced trace points, which is like in kernel you have like in the source code trace this point, and these are the trace points, and it provides some arguments. Then they decided that you don't always want to parse all of the arguments, so they introduce row trace points, where you just access the information you want, so you don't pay the extra cost of parsing all of the arguments if only you need some of them. After that, I think they introduced fentry, fexit, and it's called, I think, tracing type of the program, which actually has some trampolines. So
Essentially, it's very, very fast because you don't pay a lot of
yes.
costs, and you can inject the execution directly into specific areas of the kernel, so usually you use cell time for
Yeah. Any other questions? Oh. Okay, in that case, thank you.
Thank you.